Hi all, and welcome to the Medical AI Lab session. Today I'm delighted that we have Oishi Banerjee talking to us about Unified I/O, a unified model for vision, language, and multimodal tasks. This is work from Allen Institute for AI and UW in Seattle. Thanks, Oishi. Take it away.
Sure. So yes, as Pranav just mentioned, we're looking at Unified I/O, which unifies vision, language, and vision language multimodal tasks. So to start off with, for some context, a lot of natural language processing tasks are currently unified. And what do we mean by that? Well, I'm talking about, I don't know, is this sec to sec or is it seek to seek? I'm not sure how that's pronounced.
Seek to seek.
Seek to seek. All right, so there's seek to seek, and the entire procedure here is that you have a lot of tasks that have a text input and a text output. And you take the text input, you tokenize it, you pass the tokens into a model such as an encoder decoder, and the model outputs another sequence of tokens, which you can then convert back out to text. Now, this particular setup applies to a huge range of NLP problems. Some examples are on the side: language translation, text summarization, so on and so forth. And the reason why this is useful is that it allows you to unify tasks. So what that means is essentially you can have one model that does language translation and text summarization and and question answering. So as a result, you don't have to have a lot of different custom model parts in order to have one model that does a lot of different tasks. Now, by contrast, we have computer vision, which is a bit more chaotic. It's a bit more, it's got more moving parts. For example, here's a common setup for if you're trying to do multiple different computer vision tasks. Oftentimes, you will have an image and you'll pass it through one unified backbone. And what that backbone will do is it'll give you some features. It'll be a feature extractor. It'll give you an embedding of that particular image. But it doesn't go directly and give you an output. Instead, you have to have some sort of custom model section, which will take in the sort of generalized embedding and then get you the exact kind of output that you're looking for. Now, for example, that output might look like a lot of different things. It might look like a bounding box in the case of object detection. It might look like segmentation maps in the case of segmentation. And so there's a lot of variation potentially around what these outputs might look like. And that variation makes it hard to have one single model that can handle a lot of different tasks at once. So the goal of this particular work, Unified I/O, is to get rid of all of those custom parts for all of these different vision tasks, and instead use the seek to seek procedure, but apply it not just to the NLP, but also to vision and language, vision tasks as well. So the idea here is that instead of tokenizing just being a thing for text, you can tokenize images. So in this particular case, here's a multimodal task here's a task that involves both vision and language. As a standard over in NLP, you take in some text. You'll notice that we have both a prompt specifying what kind of task, as well as the actual text input. It'll go ahead and tokenize it, run it through the model, produce a series of tokens. But the innovation here is that that series of tokens doesn't have to represent just text anymore. It can represent an image, and therefore you can handle vision outputs. So they use both the prompts and, more importantly, seek to seek for images in order to unify a really large range of vision and language tasks. And they end up creating a massively multitasked model. To put this in context with some other papers, because we've talked about a couple of different models which are attempting to unify large ranges of tasks before. But to put this in context, Gato and Flamingo, which are other names that you might be familiar with, they don't unify vision tasks. They don't deal in visual outputs because of this issue. So Unified I/O goes ahead and makes it so that you can tokenize images as well. To get into a little more detail, here are the technical details of exactly how they tokenize each data type that they handle. For language, they use sentence piece, which I believe is fairly standard for NLP. Now for images, they use a autoencoder, specifically it's VQGAN, which is recently shown to do well. And then they also handle image coordinates. And in order to tokenize image coordinates, they just make a custom finite set of image coordinate tokens. For example, they just say lock 0 represents, 0 on either the X or Y axis. So therefore, if you wanted to represent the point 0, 0, the top left corner, you just say lock 0, lock 0. And that's just a custom finite set of tokens that they created. So here are some examples of some of the tasks that that Unified I/O tackles. Here we have image-to-image tasks. You'll notice that first of all, they have a prompt, which is how they're specifying what exact task they want to be done. For example, they have what is the depth map of the image. They put in an RGB image that gets tokenized, passed through their model, and then it produces on the other end. What it actually produces is a set of depths. For each pixel, they say, oh, we think this is 3 feet away, 4 feet away. They then have a mapping procedure to take those depth measurements and convert them to RGB, which is how you get this grayscale image that they have here. Then they have the sort of similar process for surface normals, where once again, you pass in an image. What you actually get back is, I think, a list of angles that at this pixel, we think that the surface normal is at this particular angle. Once again, they have a mapping, which takes those angles and converts them over to RGB so that you get a nice visual output. Here's another case of image to image. Here, this is image synthesis from a segmentation. You'll notice that the prompt here actually is a bit more complex. They've got a lot of information loaded into that prompt about what each color is meant to mean, like what type of material it refers to. Once again, I think it's giving pretty reasonable results. Meanwhile, they also handle pure NLP tasks. That's perfectly doable here. This is an example of pretty standard reading comprehension question answering. Then when it starts to get a little bit more interesting is you can mix and match. You can have image to text. In this particular case, they're doing image classification. And the way they handle image classification is they go, imagine you have a data set that has 1,000 labels. You pass in an image, and then you go and find the log probability of any particular label from that data set applying to this image. You find the one with the highest probability, and that is your answer. That's how you get your top one prediction on an image classification task. All right, so to spice things up, we have image generation as well. So this is a case where we're doing an image output. We also have multimodal tasks where you take an image plus text. So you can do basically visual comprehension of images. And finally, the most multimodal of all of the different tasks is you've got things that have image text outputs as well as, image text inputs as well as image text outputs. For example, here you might have a prompt of what color is this band? You have the image. It gives you both a text answer, but also a segmentation map that visually represents your answer. So in terms of what's going on the model side of things, it's actually pretty standard. It's a T5 transformer. They have 4 different sizes that they worked with here, ranging from the smallest, which is 71 million, to XL, which is 2.8 billion. And in the entire training and validation process, what they really hammer home is they are interested in having a multitasked model, a model that is extremely versatile, that doesn't necessarily need to be fine-tuned. So they pre-train on pretty standard mask to image denoising, text band denoising tasks. They train on literally 80 different data sets. So there's a lot of, there's just a lot of coverage of different types of data, different types of tasks in the training process. And then they validate once again on both the GRIT benchmark and then 16 other data sets. And the notable thing about their validation is that they don't fine tune. So there's no fine tuning experiments in this paper whatsoever. The idea is that this model should give you pretty good performance on a huge range of tasks right out of the box, and you shouldn't need to do a lot of customization. So In order to dive into their results, here is the results that they got on the GRIT benchmark, which has, I think, 7 different image tasks built into it. One notable thing that they mention is that out of all of the models which have been tested on this benchmark before, they are, of course, the first to be able to do all of the different tasks. Previously, people had to like pick and choose what their model could actually handle. In general, they are receiving state-of-the-art performance on their Excel model. So their Excel model does seem to be, state of the art. There is an exception here. On the surface normal task, they do poorly. And yeah, they're not state of art on the surface normal task. Their explanation for this is that they think that potentially the autoencoder that they're using for tokenizing images potentially is not quite fine-grained enough, and that you need really fine-grained image representations if you're going to do surface normals, because there's tiny fine-grained differences in angles. So they predict that in future work, if you went ahead and put in a more fine-grained, more powerful autoencoder for handling image tokenization, they suspect that they'll see higher performance on the surface normal task. Beyond that, another interesting thing to notice here is that in general, performance is increasing as you increase the size of unified I/O. So it really does not seem like they have saturated performance yet. If you were to just take the same model architecture, make it even bigger, add even more parameters, add even more layers, you would probably still see performance go up. In addition to that, we have a whole bunch of other benchmark data sets that they tested on. You'll see familiar faces, you'll see ImageNet, you'll see Coco. And here, they are not really achieving state of the art, but I would say the performance is respectable. The way, at least the performance of their Excel model is respectable. And the way that they justify that is that they didn't fine tune. They said that they expect, had they fine-tuned or had they modified the training process to, take advantage of some known data set specific tricks, they say that you probably would have seen state-of-the-art performance. So take that as you will. It seems like it does pretty well out of the box. So in order to go over some future directions that they mentioned, I think these have been foreshadowed already, but number one, they are interested in fine-tuning this model. That's something that they completely left for future work. This paper only looks at out-of-the-box performance. Presumably, you would start to see more. You might start to see more state-of-the-art performance on those other data sets once you went ahead and actually fine-tune the model. In addition to that, they said that there are some data augmentations that they could have made more complex. They could have apparently there are some data augmentations that are known to really improve performance on specific data sets, and they said that we didn't do any of those tricks. That's how they characterized it. So again, presumably, had you pushed the augmentations further, you might have seen higher performance on the final validation results. Additionally, we saw that performance has not saturated. As you increase model size, you are still seeing major gains in performance. So that is certainly an option. And then finally, having a stronger autoencoder for image tokenization that can handle more fine-grained differences would help, especially on the surface normal task. So yeah, that is the Unified I/O paper. It's actually pretty simple once you get the idea of image tokenization. Let me know if you have questions.
Thanks a lot, Oishi. Thanks for the fantastic presentation.